Good evening. Today we will discuss enzyme kinetics. Okay, so first important thing is that you should know how to take K equivalent out, right? So it is something which is the product by the initial thing. So it's, for example, if you have 20 millimolar of glucose 1 phosphate and the final product is glucose 6 phosphate. So glucose 6 phosphate divided by glucose 1 phosphate. So that is your K equivalent, that is 90. If you want to calculate standard free energy change, that is del G minus RT ln K equivalent. Now, important thing is that this thing is change and this is actual free energy. Means delta J would be for delta free energy change plus RT ln C, that is the product here. This is divided by the object. As it has A, it will come into power. Now, if the reaction is at equilibrium, your delta G would be 0 and therefore this equation will come into being. Okay, so that is more important thing. Now, the important thing is that if the delta G is very large, then the reaction would be if the reaction is negative and very large, then the reaction is very favorable. And this is what the activation energy that people talk about, right? This thing is very independent of the pathway. It only depends upon the initial and the final product, and it is additive in the nature. Now, the most important thing is that what we do is that this is the transition step. But what an enzyme will do is to reach to the state of product formation, it will form several small steps in order to reach towards the product. So therefore, it lowers the activation energy, but nothing else is done. So your enzyme creates small several energy barriers rather than one single large one. Now, binding energy. It's very important that you understand that the energy which is being released is the energy that the enzyme binds in its substrate, especially during the transition state. So once it's broken down, that kind of binding energy, which is the bond energy, or maybe in terms of charges, the way they are interacting, that is the kind of energy which is being liberated. It doesn't change overall free energy difference between substrate and product. Now, if there are like two molecules bimolecular reaction, then the rate constant is in second order. So it's very important that if there are two groups, three groups, then the less freedom of motion would be there, and therefore that will somehow impact your spontaneity, right? Now, there are two distinct behavioral things that you should consider. At the first order, if you have enough substrate, like for example, this is V naught S, it is somewhere linear if you have limited substrate. But if I increase the substrate to a, very big thing like this, you will understand that the enzyme is something which is limited and the binding sites are also limited. So these free substrates will not do anything in the reaction. But here, the substrate will go and bind and form an ES complex because the binding sites are even formed. So it's directly proportional to ES. That is K2 ES. Now K2, we will understand it. It's the catalytic thing, which is the slowest step in the reaction. Therefore, it will determine the rate. Now, here we can talk about that these are like, it's very high. Yes. So practically all enzyme is logged in this. So adding more substrate will not change the reaction velocity. So this is strictly limited by the chemical transformation. So it will depend upon ES rather than S. I hope that thing is clear. Now the foundational assumptions, there are two assumptions, which is rapid equilibrium model and quasi-state assumption model, which is Briggs and Henling. Why? Let's understand. So the reaction that is given to us is something which is, you can add the bottom. This is the concentration thing. So K1, K minus 1, it forms an ES complex, and therefore it forms, after catalysis, it forms a product like somewhere equals P, right? So the important thing is that what Michaelis did was he said that it reaches an equilibrium, right? And we assume that the dissociation is much faster than catalysis. So it will move backwards. And therefore you can equilibrate this with this. So expression was this. However, it's a very, valid for limited places, right? You always have to assume that this is larger than this. So it's very different thing that you have to have incredibly slow formation of this rather than you have to say, okay, the dissociation has to be fast enough. So Briggs and Helden came out with quasi-state model that the reaction remains. This ES is the determining factor. This ES is the determining factor. So he just said that this DES by dt will remain constant. This was his assumption. Okay. Now this is maximally valid upon this key. When this will form, only then this thing will form, right? So this equation that came into being, let's discuss this equation first. That K1, because the thing that is favoring this will be in positive sign, minus of K minus because it's going backward, minus, it is going away from ES, so it will be also minus ES equals to 0. Now from here it comes the Michaelis-Menten equation. We call it Michaelis-Menten equation because of the fact that it goes into this KM equation, which is Michaelis-Menten equation. Now, how we derive it, it's pretty simple. Okay, let's go through this once. So the total enzyme, can I say this? Right? You can add this concentration brackets, pretty important. Why? Because whatever free enzyme, whatever substrate enzyme, that would be the total enzyme. So if I say that I want to find the E, it would be ET minus ES. Okay. Now, as per this Briggs and Helden thing, which we got into understanding, this is the equation will be formed because one was in, these two were in the negative direction. Now let's understand it. So K1 S equals to K minus 1 plus K2 S. Now, just replace this thing. Right? Once I replace this whole thing, it's very important that I am just reducing certain values. This would be S. Now, Kn, I'm assuming this divided by this is Kn to shorten the equation. Now, what will happen is that take this ES, entire ES towards this side. Okay. Now, just a second. Okay, whatever. Now, what you will get, ET S equals to Kn plus S by Es. Now, your V naught will depend upon the substrate, right? And your V max, that is the maximum velocity that it can depend, would be K2 but it will be equal to enzyme total because all of it will be converted into a product, right? Now, if I just replace it, what I will get? Mm. So this would be max if I'm replacing here, right? K2 substrate Km plus what is Es? S, what is V naught? This S is for everything, right? So it is Es by K2. I'm sorry, V naught by K2. So K2 will be cancelled and you will get Vmax. I'm just making this equation towards this side. Dot S by Km plus S is equal to V naught. So this is your derivation for the equation. Okay. Now the graph that I want to make you understand is here that during the initial substrate concentration, you can find it somewhere linear, right? Because it is directly depending upon the substrate. But if your substrate goes beyond the concentration level, you don't know where the Vmax will end up, right? The enzyme total will be formed, but we don't know where it will end up. So that is extremely difficult to understand that where exactly this Vmax is located. So people came out with different form of equations. One was the Berg solution where they just did was that they took as equal to y equals to mx plus c. They just reciprocated the equation, as you can find that this equation is somewhere like this, right? Okay. Vmax is Kn plus S equals to V naught. Once you take the reciprocal of it, 1 by V naught equals to Km by Vm, right? And as you know, this will be 1 by substrate, and this is also divided by 1 by S, so it will be 1 by V max. So you can find that this is exact reciprocal of the equation once you just reciprocate it. So what happens is that here it is 1 by S, y equals to m x plus c. So 1 by V max is the intercept, right? This this is the slope, right? And this is what we plotted. Now, this is the graph that we are getting. But the issue with it is that, yeah, if you take minus of 1, okay, you get the equation here because important thing that I need to make you understand that it's going straight, right? And here the things are collided. So if there are errors in this portion, then there would be so much error because the equation was going, now it's going straight line. So it's dependent upon this substrate thing, right? This Vmax, it's going straight, right? So like if the graph is there, then the Vmax will also go in this direction, right? So there, everything is very clustered here, even the S thing. So if there is an error here, then there will be error here. So that is what they took into.